Let's work through an example of this, returning to our now classic copper-silver galvanic cell, asking what is the standard potential of this copper-silver galvanic cell? I won't go all the way back to the schematic of the galvanic cell. You're more than welcome to drop back to that video if you want to. Here's the cell notation for that cell, with copper undergoing oxidation to copper 2 and silver 1 undergoing reduction to silver. Now, what we can do with each of these half cells is first, and I highly recommend this, write the half reaction that's occurring in that half cell in the sense that it's occurring. So for example, in the copper half cell, which is the anode, copper is undergoing oxidation to copper 2 plus and 2 electrons, and on the silver side, in the silver half cell, silver 1 is undergoing reduction to form silver metal. To determine the overall standard cell potential for this cell, we're going to apply an idea we've seen previously. Now that we've generated and we understand the standard reduction potentials, we can really zero in on this equation and realize that the standard cell potential is the difference between the standard reduction potential for the cathode's reduction half reaction and the standard reduction potential for the anode's reduction half reaction. And that's where things get just a little bit tricky right here with the anode. But essentially, we're going to calculate the cell potential as a difference between the electrode or half cell potentials. So let's return to the problem and see how this works. Well, first, we need the standard reduction potentials for copper 2 and silver 1. And we can grab those from our table of standard reduction potentials here, for instance. So for copper 2, that reduction potential is positive 0.34 volts. And for silver 1, that potential is positive 0.8 volts. So let's go ahead and jot those down. So the standard reduction potential for copper 2, 0.34 volts. The standard reduction potential for silver 1 going to silver is 0.8 volts. And it's good practice to list both the oxidized and reduced forms, and I actually recommend in this order, with the oxidized form on the left and the reduced form on the right, in the parentheses, so that we know exactly what we're talking about here. We're talking about the reduction potential of copper 2 plus when it forms copper 0, and the reduction potential of silver 1 plus when it forms silver metal. For metals like iron that have multiple stable oxidation states, this can get really tricky. So it's important to list both components in the half cell, I think, when you're thinking about reduction potentials. In any event, let's think now about how we will put these together to determine the cell potential. First, let's take a moment and write the overall balanced redox equation. And to do that, we're going to need to double the silver half reaction, since I need 2 electrons over here, since 2 electrons are lost in the copper half reaction. This is how I end up with 2 Ag pluses and 2 Ags. This may give you the idea that I need to double the standard potential of the silver half cell, the standard reduction potential for silver 1, in calculating the cell potential. But not so. And this is one of the really nice things about the standard reduction potentials. You don't need to scale them, even if you have to scale a half reaction to produce the full-blown balanced redox equation. The reason has to do with the fact that when you double a half reaction, you're doubling the energy associated with the half reaction, but also doubling the charge transfer, doubling the number of electrons, right? So the ratio of energy to charge remains the same when you double or triple or scale by any value. So the standard reduction potentials are unaffected by scaling, which is really nice. Keeps things simple. All right, so now we can apply this idea that the cell potential is the difference between the reduction potential of the cathode and the reduction potential of the anode. And we've already listed these values. It's 0.8 volts for the silver 1 to silver reduction and 0.34 volts for the copper 2 plus to copper reduction. Notice here, being very careful, this 0.34 volts corresponds to the reverse of this process, reduction of copper 2 with 2 electrons to form copper metal. This is why a negative sign shows up in this equation. So there are a couple of different ways to think about this equation, actually. And it's possible, for example, to think about it in a Hess's law sense, that we're reversing the reduction reaction to produce an oxidation reaction, and that's why we flip the sign of the reduction potential here. That's an equivalent way to think about this equation. But the potential difference way works as well, and I've actually used both over the years. So you can do whatever works for you here in terms of thinking through this. But in any event, 0.8 volts for the reduction process, negative 0.34 volts for the oxidation process, and so the overall cell potential is 0.46 volts. And one way you know that you've done this correctly is that this value should always be positive. If this value comes out negative, there's a good chance that you've confused the cathode and anode. In fact, this is one way we define or recognize the cathode and anode. The cathode and anode are set up such that the cell potential comes out positive. This is always true for a functioning galvanic cell. Now, with that said, we can write any old redox reaction in either direction, right? And so a given redox reaction may not necessarily be spontaneous in the way that it's written. And we can conceive of a cell potential for any redox reaction as it's written. If that cell potential is positive, then the reaction as written is spontaneous. However, if you think about what happens if we flip the reactants and products of that reaction, well, we've made the reaction non-spontaneous, clearly, since if the forward reaction is spontaneous, the reverse reaction must be non-spontaneous. And we've also made the E cell negative, since in a Hess's law thermodynamic state functions kind of sense, we have flipped the sign of E cell. So reactions with positive cell potential are spontaneous. Reactions with negative cell potential are non-spontaneous. And a simple way we can think through this is to look back at this copper-silver redox reaction. The oxidation of copper to copper 2 plus by silver plus, reaction of Cu metal with Ag plus to produce Cu2 plus and Ag. This is a spontaneous process, and we just worked out that the cell potential is 0.46 volts. But watch what happens if we replace or exchange the roles of the reactants and products, if you like, right? If I take these products and make them the reactants, and I take the reactants and make them the products, I could go through the whole process of thinking through the half cell potentials and all that jazz, or I could just recognize that I have flipped the reaction, and E cell, because it's a state function, will have its sign flipped as a result, to conclude that the cell potential here would be negative 0.46 volts. And so this is a non-spontaneous redox process, and the negative cell potential helps us see that. If we wanted to get this to go, we would have to apply a voltage of positive 0.46 volts at a bare minimum, in practice quite a bit higher than this. And we'll see how that works in a later section, actually, when we talk about electrolysis, which is used to drive non-spontaneous redox reactions. So it is possible to push this toward the copper side, but we need an external circuit and an external source of electrical energy in order to do that.